Can you see the screen now?
Yes.
And
So
can you see
welcome.
my
Yeah.
pointer here?
Yes. I can also see the point.
You can see the
Yeah.
okay.
So welcome everybody again. So for the second talk of the week, and we are having Professor Kinya Oda from Tokyo Women's Christian University, and he's going to talk about emergent quantum gravity from irreversible Vierbein, a scale invariant realization. So let's begin, and maybe I will send you a reminder when 5 minutes are left.
Okay, thank you. So personally, actually, I don't like to listen to online seminars because it's so hard to, you see, make questions. So I think uh, it would be nice if you could stop me at any time you want and give any question. Okay. So let me start. And now you can see the screen. I don't see any face.
Yes, so we can see the screen and also your mouse.
Okay. So I asked ChatGPT, O for mini high, to draw an illustration for this talk. And I got this. Well, it's not quite brilliant. And then I asked something more cute. And then I got this. Doesn't look like so nice. Maybe some style, not at all. And then I asked for some Ghibli style with more relevance to the talk, please. And I got this. So, well, anyway, I'll talk about something like this. Okay. So this is the plan of my talk. First, I emphasize the importance of local Lorentz symmetry when considering gravity, especially when considering matter or spinor field in universe or in curved spacetime. In the second part, emphasize the connection, relevance. How do you say? Correspondence, or how do you say? Resemblance of Vierbein to a Higgs. And I show some postulate, which we call irreversible Vierbein postulate. And I show how spacetime emerges from this kind of scenario. And in the third part, I show another concrete example of having classical scale invariance and show how spacetime and Planck mass can be generated from this kind of scenario. Okay. Key, cons- Key concept is local Lorentz symmetry, and to look at gravity as local Lorentz gauge theory. And let me first introduce the standard model. I think you have all seen this kind of plot. The horizontal axis is the particle masses that couples to the Higgs. This is top quark having 170 GeV, Z 90 GeV, W 80, bottom, tau, and recently charm is now observed also, and mu. And you see the standard model is getting more and more precisely describing the nature. Vertical axis is the coupling, measured coupling of the Higgs to the top, Z, W, bottom, tau, mu, all consistent with the standard model. And in the standard model, most degrees of freedom are spinors. If you count the number of degrees of freedom, 90 out of 118 degrees of freedom are spinors, namely quarks and leptons. So roughly 3/4 are spinors. On the other hand, the standard model cosmology has become precision science. Just 6 parameters beautifully fit hundreds of data points, as you have seen, I think. So in some sense, to describe nature or our universe, it is crucial to define spinor in curved spacetime. How? How to define spinor in curved space at all? Actually, spinor is not a non-trivial representation of diffeomorphism. So it just transforms like a scalar under diffeomorphism or general coordinate transformation. And spinol is just a local, so spinol transforms non-trivially under local Lorentz transformation that is defined on the tangent space of the manifold. So we need local Lorentz symmetry to define spinol field. And this is just a backup, so I can skip. And this is another backup to discuss the difference between DFL and GL4, but this is again just backup. So to repeat, and to write down the spinol field, we need to obtain, we need to write in terms of the local Lorentz transformation. And for that, we need Vierbein. It is necessary to define spinol at all on curved space. As I said, it's spinol field transforms non-trivially under the rotation of the basis of the tangent space. And roughly, that Vierbein is derivative of the local Lorentz coordinate, locally inertial frame with respect to the space-time coordinate, roughly. And Vierbein is, so in this sense, more fundamental building block than the metric. So Vierbein is constructed, metric is constructed from Vierbein, and Vierbein is necessary to define spinol fields on curved space-time. And under local Lorentz symmetry, the Vierbein transforms as a fundamental representation. So just like Higgs transforms as a fundamental representation under the gauge symmetry, like SU2 and so on. And as I said, this local Lorentz transformation is roughly local rotation of tangent space basis. And to have such local symmetry, we need to introduce gauge field, which we call local Lorentz gauge field, omega. And for example, covariant derivative on local Lorentz vector is just an ordinary derivative and the connection. So this AB is the indices for the local Lorentz transformation. And roughly, gravitational connection, gamma, is obtained as the combination of local Lorentz gauge field, omega, and some derivative of Vierbein. And this transforms the same as Christoffel symbol. And and this line is not related to the main development of the talk, but variation with respect to omega gives you the variation with respect to the connection. So from this kind of perspective, Palatini formalism seems to be more preferred as gravitational theory. And actually, this kind of difference makes difference in the observables if you consider, for example, Higgs inflation. So this is the first part of my talk. Any questions so far? It's okay.
I don't see any questions.
Okay. And please stop me at any time. Okay. And in the second part, I discuss the resemblance of Vierbein and Higgs. And I show how space-time emerges from irreversible Vierbein postulate. So The Einstein-Cartan theory is the theory of local Lorentz gauge symmetry. Local Lorentz gauge symmetry is nothing but SO13 symmetry. And action invariant under the general coordinate transformation or diffeomorphism times SO13 can be written like this. So this F is the field strength of SO13. And unlike the ordinary gauge theory, we have Higgs or fundamental representation that is space-time vector. That's the big difference. So we can have the single field strength term invariant under these symmetries. And this term becomes the Einstein-Hilbert action in the end. And this is just cosmological constant. And as I said, this is the field strength from local Lorentz gauge field. And classically, if you vary the local Lorentz gauge field, we obtain the relation between local Lorentz gauge field and the Vierbein. And this F, local Lorentz gauge, local Lorentz field strength becomes Riemann tensor. Oops. And this is the point I mentioned before. Difference is not merely theology, mere theology. Whether or not local Lorentz gauge field omega is independent degree of freedom makes physically observable difference for Higgs inflation for the same Jordan frame action. And well, this is the point just to re-emphasize, as I said, what I said, peculiarity of the gravity. So matter in local Lorentz fundamental representation, that is Vierbein, is a space-time vector. So the lowest power of field strength is F, not F squared. So up to this order, there is no kinetic term, only one derivative between bosonic fields. So both Vierbein and local Lorentz gauge field are auxiliary fields. And once you integrate out one of them, then the other acquires kinetic term. And in our case, we will see that this local Lorentz gauge field becomes heavy and integrated out. And then Vierbein acquires kinetic term in the end. And one problem is there are too many connections. For DFEO or general coordinate transformation, we can introduce, for example, GL4 gauge field or a Levi-Civita connection made of metric. For local Lorentz, we can introduce local Lorentz SO13 gauge field or Levi-Civita spin connection made out of the Vierbein. And also there are too many terms you can write down in this kind of construction. So we want to have some way to control these possibilities. And here, the question is, what is right weak field limit in gravity? In Higgs, the nonlinear realization is the expansion around some fixed wave. And in the nonlinear realization, the weak field limit gives you, in the weak field limit, Higgs field becomes its wave. In linear realization, Higgs field becomes zero. So in the standard model, the weak field limit is the limit to a symmetric point. In gravity, conventional weak field limit is the limit to some fixed or some given non-zero background corresponding to the nonlinear realization in the standard model. Here, what we assert is that the weak field limit of gravity must be the vanishing Vierbein. Actually, this was first, as far as we know, first claimed by Florealini and Pelcacci. And also, it's said that this kind of limit is involved when the topology change of the spacetime becomes relevant at Planck scales by Zeitlin in 1982 and by Horowitz in 1991. So, and in the Higgs mechanism, for example, we do not put the inverse of the Higgs squared. And actually, this kind of term is perfectly consistent with any symmetry of the standard model. And at low energy, this is even more relevant than any other term. And only weak field limit, Higgs going to 0, is the logic to kill this kind of term by hand in the standard model. And given the success of the standard model, we argue that this is the same, this logic applies to the gravity at the cutoff scale. So consequence is that inverse matrices, G inverse mu nu and E, so this is inverse of the original inverse of the original Vierbein is absent at some scale. Okay, and this is kind of summary. The Vierbein is a SO13 fundamental representation. And this is space-time vector having index mu. And the wave of Vierbein indeed leaves background symmetry. That's a difference. So up to here, things are the same here. Higgs is also a fundamental representation of the gauge symmetry, transforms the similarly. But Higgs is a scalar. And Higgs wave breaks the symmetry, whereas Vierbein wave leaves background symmetry. Indeed, the local Lorentz gauge field mass term is invariant under background local Lorentz symmetry, whereas gauge mass term breaks the symmetry once Higgs acquires the wave. And the assumption made in the standard model is that there is no inverse term of the Higgs field, even though this is perfectly gauge invariant and even more relevant at low energies. And this corresponds to the irreversible Vierbein in the gravity side. Okay. And if you postulate irreversible Vierbein at some scale, then no kinetic term for scalar and vector are allowed, because inverse is prohibited both for Vierbein and for the metric. And well, maybe so the key assumption may be restated that length, line element, is more fundamental than the derivative or momentum. At Planck scale, where topology change wormhole loops become significant. So this is the works that I mentioned before. And if you postulate this kind of if you demand this kind of existence of this kind of weak field limit to prohibit this kind of term, then there are allowed only 3 terms at a scale. One is the cosmological constant term like this. The other is the spinol kinetic term like this. Actually, this term contains inverse of the Vierbein, but this cancels out with determinant of the metric. And also, the other term allowed is the Einstein-Hilbert term. And this has two inverse Vierbeins, but these two cancels out in the with the determinant of the Vierbein. And in general, these coefficients, this one and this, and also z factor of the fermion, these can be a function of scalars, like phi, psi bar psi, and so on. But anyway, kinetic term is allowed only for spinols. So it's like putting compositeness condition at lambda uv. And the local Lorentz gauge symmetry is regarded as a hidden local symmetry of the strong interaction. And hereafter, we compute the around the flat background because this is the simplest to compute. So we put simplest flat background on that. So Vierbein, background Vierbein is proportional to the flat spacetime metric times conformal factor C. And we will see that local Lorentz gauge field acquires kinetic term once we assume this kind of background. And unlike the ordinary gauge field, ordinary Higgs mechanism, longitudinal component of the local Lorentz gauge field appears also automatically. And also we will see that Vierbein effective potential emerges in a sense. First, we talk about the generation of kinetic term of the local Lorentz gauge field. So ordinary scalar and gauge kinetic terms will be generated just as in the hidden local Lorentz symmetry, hidden local symmetry in the hadron theory. And the question is how about Vierbein and local Lorentz gauge kinetic terms? And here we pick up local Lorentz gauge kinetic term. And at the end of the day, you end up with this kind of expression. So the transverse mode and longitudinal mode. And transverse mode appears, I mean, the mass term of the local Lorentz gauge field appears both, at the same time appears both for transverse and longitudinal part. So kinetic term is generated, how you say, the transverse mode and longitudinal mode appears at the same time for both the the fermion loop induces the transverse part and longitudinal part at the same time. That's a quite big difference. And also, this term appears as a finite correction. So, and this is the first. For the first time we found the finite correction to this kind of local Lorentz gauge kinetic term. Beforehand, people used the zeta function regularization, and also sorry, I forgot the name, but anyhow, people look at only divergent part and concluded that these terms are not present. But we have computed the finite correction and obtained them to present, both in the cutoff scheme and in the dimensional regularization scheme. And peculiarity is that spinol loop directly generates longitudinal part, even without gauge field mass, which evades Weinberg-Witten theorem. And both quadratic and logarithmic divergences cancel out miraculously in local Lorentz gauge kinetic term. And so the result is obtained as a finite correction. And we have also computed Vierbein effective potential if we employ a cutoff scheme that does not preserve the general coordinate invariance. So that is allowed only around the flat background, then we obtain some logarithmic correction to the Vierbein background. Okay, so this C is the conformal mode. This C is the conformal mode. MF is the fermion mass. Lambda CC is the cosmological constant. Lambda G is the scale where a cutoff scale, or the scale where we assume we put the irreversible Vierbein postulate. And if we put the tree level cosmological constant, this kind of logarithmic correction makes the potential run away at very high field region. And this is the result if you employ the cutoff scheme that does not respect the general coordinate invariance. If you employ cutoff scheme without that respect general coordinate invariance, we have that only have term c to the fourth. So only we only have renormalization of the cosmological constant. And general coordinate invariant cutoff gives, so V is proportional to the c to the fourth. And so the potential gets either runaway or symmetric. And runaway may indicate expanding universe. And also another point is we don't have any graviton mass term, so symmetry is preserved. Background differ and local Lorentz are preserved. And local Lorentz gauge mass term is invariant under background Lorentz, local Lorentz transformation. This is backup. Maybe I can skip. So I turn to the last part. So in the last part, I consider, by the way, how many minutes did I use?
We still have 20 minutes. 15 minutes. 15 minutes.
15. Then maybe I can I can talk a bit more. Okay. So then I think I should talk about the number of degree of freedom. Just a moment. So diffeomorphism or general coordinate transformation has 4 degrees of freedom. On the other hand, the local Lorentz transformation has 6 degrees of freedom, like SO4. So totally there are 10 gauge degrees of freedom. And at the classical level, the Vierbein has 4 legs, so 16 degrees of freedom. And indeed, the local Lorentz transformation has 6 degrees of freedom. So 6 among these 16 are Namb-Goldstone modes corresponding to the SO13. And the remaining degrees of freedom is 10, which corresponds to the degrees of freedom of metric. At the quantum level, these maybe you already know, but 10 degrees of freedom among 10, using transverse condition for differ, you subtract 4, and for ghost degrees of loop subtracted, and then 2 is remaining. And actually, this pattern is different from the induced gravity GL4 to SO13. So here, what we impose is both TFL and SO13 from the beginning. Okay. So up to this is about first paper of our first paper, and the third part is about our second paper. Here we assume a classical scale invariant action, so-called, and then we see how space-time and Planck mass are generated from it. So here we consider space-time and Planck mass generation. So action is again the integral and determinant of the Vierbein, and this is spinor kinetic term, and this is the kinetic term, and this is Yukawa between scalar and spinor. And since we have scalar, now we can write down the scalar squared times the would-be Einstein-Hilbert. And then we can have quartic term of the scalar. And here there is no mass parameter. And this kind of classical scale invariance can be realized, for example, from the multi-criticality point principle, which we discussed in a different context. So how do you say? One may argue that classical scale invariance is fake because anyway it's broken by quantum level, but there's some mechanism that realizes this kind of action. And so what is allowed by symmetry and classical scale? So essentially this is merely saying that there is no no parameter having mass dimension. There's only dimensionless couplings, lambda, z, and and y, Yukawa y. And what is allowed is the spinor kinetic term, and Yukawa, and Einstein-Cartan, with dressed with scalar field. So it's like no minimal coupling in the Higgs inflation, and the quadratic term of the scalar. And again, scalar kinetic term is not allowed here at this scale. And here you see that scalar wave becomes the Planck mass at the end of the day. Okay. And now we skip to the result. So here we employ a GC invariant regularization. So that corresponds to, where was that? This part. So general coordinate invariant regularization. So more, how do you say, authentic regularization. And then again, we obtain the runaway potential for the conformal mode of the metric. So this is the direction of the conformal mode. And this is the direction for the scalar. And you see that there's no conformal mode square. So graviton remains absolutely massless. And you have a runaway potential for the conformal mode. And for the direction of scalar, you can have some wave of the scalar. So Planck mass is generated by the scalar field. So yeah, maybe I quit a bit fast, early. So here I summarize and give some discussion. In the first part, I emphasized the importance of local Lorentz symmetry. And this is essential to write down a matter field in the universe. In other words, it's essential to write down spinor field on the curved space, in the curved space-time, on the curved space-time. And in the second part, we argue that if you consider the Higgs field in the standard model, it is quite natural to argue, to regard the weak field limit of Vierbein as the zero field limit, which leads to the irreversible Vierbein postulate. And we have shown how possibly spacetime can be emerged from this kind of setup. In the third part, we further imposed a classical scale invariance. And then we have shown the Planck mass and spacetime can be generated from this kind of setup. And discussion is that if runaway conformal mode really indicate expanding universe or not. In a model, for example, in some Higgs inflation model with nonlinear sigma model, the fluctuation of the conformal mode having wrong sign kinetic term is shown to decouple from scattering in a model, in the model. So this kind of decoupling, so it would be interesting to check if this kind of decoupling occurs in our model or not. And as I said, among 16 Vierbein modes, 6 Vierbein energy modes are eaten by local Lorentz gauge field, and 10 are left as graviton mode. And now we are trying to see it more explicitly. I mean, to show it more explicitly. And another problem is, after having fermion loop, there are so many forms of Vierbein kinetic terms. So we don't we are looking for some way to control this kind of to control this kind of terms. And one of my collaborators, Masatoshi Yamada, is great fan of asymptotic safety. So, well, we are. So it will be, and he's thinking of considering UV theory, considering if UV limit of this theory is asymptotic, can be asymptotically safe or not. Well, that's all. Thank you.
So thank you for the nice talk. Any question from the audience? Please unmute yourself and ask. Okay, I have one small question, and that is basically related to the usual graviton scattering. So, in the usual graviton scattering, we know that it basically blows up in the Minkowski space, right? Even if you modify the UV. So, in this picture, how do you imagine that story to play out?
So this is here we just regard this as a cutoff theory. So
Okay.
So in some sense, if you consider string theory as a quantum gravity theory, then we postulate that after integrate out all the stringy modes, this kind of theory will emerge as a low energy effective theory. Or else it could be that the really UV limit of this theory becomes asymptotically safe and allows the non-trivial UV fixed point, strongly interacting non-trivial UV fixed point that allows you to define quantum gravity. So there are several options.
Okay.
Yes.
I see. And another point is that have you thought about inflation in this picture, or does it?
Well, that's beyond the scope so far because you see we have only runaway potential so far for the conformal mode of the gravity.
Okay.
But at the end of the day,
maybe runaway potential can also do some quintessential inflation and this
would be nice,
non-oscillatory kind of inflation.
But so far this is unbounded, so we need something more.
Okay, I see.
Yeah, but it will be nice if you can consider inflation.
Okay.
Or you could even add inflaton potential to this kind of setup, because the potential itself is allowed as that does not contradict with the irreversible Vierbein postulate. You can put any potential here. So this can be any function of the scalar.
Okay. Okay, so thank you for the nice talk and the nice presentation. Will you be able to send us the slides?
Yeah. Just by email?
Yeah, I think email is fine.
Okay.